All right. Good afternoon, everybody, and welcome to the Petro-Teach webinar on hydraulic fracturing. As you already heard from the organizer, you are entering as the only listening mode and muted. Before we proceed the event, let us check if you receive my voice. There is a window in front of your platform, and by clicking on the arrow, you will see the full window version with a chat box. Please type the word hi or hello or something so that we make sure we have established the full communication. Okay, seems everything is okay. So the agenda of the event today begins with a brief introduction to Petro-Teach, and then we introduce our distinguished instructor, Jerry Rusnak, followed by a webinar lecture which lasts 45 to 60 minutes on hydraulic fracturing. And also we will have Q&A session for approximately 15 minutes. So PetroTeach is a global provider of high quality training solutions to the oil and gas industry. We are providing at the moment more than 150 training courses by up to 50 distinguished lecturers with high track record from both academia and industry. Our training styles include online, public, and in-house courses. And due to COVID-19 pandemic, PetroTeach is mainly focused on the distance learning. For more information, please visit our website www.petro-teach.com and download the course catalog. You may also follow us in social media and do not forget to watch our video in PetroTeach YouTube channel. The event today is part of the 20 webinar series that PetroTeach will be offering during year 2020. For the September, we started by Professor Bahman Touhidi on nightmare of hydrate blockage, gas hydrate blockage. Then we continued with Mustafa Haqqaq, talked about advanced petrophysics. Yesterday, Dr. Andrew Rose had a webinar on seismic reservoir characterization, and today Jerry Rusnak will talk about hydraulic fracturing. Also, 3D printing, the future of geology, will be the topic of the next webinar by Dr. Hasyuk and Dr. Ishutov. And finally, on 21st of September, Professor Wumi Iledar will talk about elements of fiscal regimes and impact on E&P economics and take statistics. So we welcome and are pleased that Jerry Rusnak can join us today. And you can see his CV. Materials to be covered in the two-day webinar are related to Jerry's valuable experience and comprehensive training on the topic. He has more than 40 years of oil field experience. He has worked in all phases of the industry, including service, supply, operations, and academia. He holds a Bachelor of Science degree in Ocean Engineering from Florida Atlantic University. He's an active member and past section president of the Society of Petroleum Engineers. So let's move to the presentation. I want to remind you all that you can post your questions using the same chat box introduced at the beginning. At the Q&A session after the lecture, they will be answered. So I'm going to hand over the talk to Jerry to address his presentation. Yes, here you are, Jerry. Yes. Jerry, we cannot hear you. I think your mic is muted.
Let me
Yes.
go ahead and start all over then. I'm sorry.
Yes, now is okay. Now we can hear you.
Okay. So what do we mean to say we are going to look at?
Jerry, the voice is not clear.
Most cases, sigma 1 overload stress, the largest stress, sigma 3, which is maximum horizontal stress, sigma stress, sigma 2, which is the minimum horizontal stress, the smallest.
We don't have your sound, Jerry.
Not sure what, can you hear me now?
Yes, yes. Now is okay. Please start from your first slide because audience couldn't hear you.
Okay. Let me go back. I can figure out how to go back here. Let me get out of this. I can't. Hang on just a second. Okay, can everybody hear me now?
Yes,
Okay.
I can hear you.
All right. Hello, everybody. My name's Jerry, and I'm your instructor today. And the course is going to be on hydraulic fracturing. And the objectives of today's course are to answer the questions. What do we mean when we say we're going to hydraulically fracture a formation or a rock? Why would we do this? When we frack, what data do we need to consider? How do we design a frac job? And last but not least, how do we analyze or evaluate a frac job? So to start out, let's answer the question. What do we mean when we say we are going to hydraulically fracture a formation or a rock? Mean we are going to apply fluid pressure to the rock that exceeds its mechanical strength. When we look at the mechanical strength of a rock, we usually look at the three principal compressive stresses, sigma 1, sigma 3, and sigma 2. Sigma 1, we usually call the overburden or vertical stress, and it is normally the largest stress. Sigma 3 and sigma 2 are the resulting horizontal compressive stresses, where sigma 3 would be the maximum horizontal compressive stress, and sigma 2 would be the minimum horizontal compressive stress. So sigma 1 is larger than sigma 3, which is larger than sigma 2. Now, if we look a little closer at these in situ or local stresses, we know from experience that a hydraulic fracture will propagate perpendicular to the minimum principal stress, which was sigma 2 in the previous diagram. And for a vertical fracture, the minimum horizontal stress can be estimated with this formula you're looking at below, where the minimum horizontal stress is approximately equal to Poisson's ratio divided by 1 minus Poisson's ratio times the quantity sigma 1, which is the overburden pressure, minus Biot's ratio, alpha, times the pore pressure, plus Biot's ratio times the pore pressure, plus sigma external, which accounts for any external stresses, for instance, tectonic stresses. So what else can we learn from the formula? So sigma min is our minimum horizontal stress. Nu is Poisson's ratio, and we can tell by looking at the formula that the larger Poisson's ratio is, the higher will be the minimum stress. Sigma 1 is the overburden stress, and again, the larger the overburden stress, which often means the deeper the well, the higher the minimum stress. Alpha is Biot's poroelastic constant, and it is tied in with the pore pressure, but just in general, as the Biot's poroelastic constant increases, then the minimum stress increases. Again, the reservoir fluid pressure or pore pressure tied in with Biot's constant shows that the higher the pore pressure or reservoir pressure, the higher the minimum stress. And if we have any external or tectonic stresses, they will again add to and increase the minimum stress. So let's look at some of these variables. Let's start with Poisson's ratio. Poisson's ratio is defined as the ratio of lateral expansion to longitudinal contraction for a porous rock under uniaxial stress conditions. The value of Poisson's ratio is used to convert the effective vertical stress or overburden stress component into an effective horizontal stress component. And this value ranges from 0.15 to 0.35 for a sandstone and 0.28 to 0.43 for a shale, which, going back to our formula, would tell us that in general, the minimum horizontal stress for a sandstone is going to be less than that for a shale. Now let's look at Biot's poroelastic constant. It's defined as the ratio of the volume change of the fluid-filled porosity to the volume change of the rock when the fluid is free to move out of the rock. It ranges between 0 for a solid rock without any porosity and 1 for an extremely compliant and porous rock. Another modulus that we use when analyzing the mechanical strengths of rocks is Young's modulus. And Young's modulus is defined as the ratio of stress to strain for uniaxial stress. This modulus of a material is a measure of the stiffness of the material. If the modulus is large, the material is stiff. In hydraulic fracturing, a stiff rock results in more narrow fractures. On the other hand, if the modulus is low, the fractures are wider. The rock is more elastic. And the ranges of Young's modulus for rocks ranges from 1 million to 10 million psi. Just for a reference, Young's modulus of steel is around 30 million psi. So we've talked about what happens when we hydraulically fracture a rock and how the properties of the rock affect this. So now let's talk about why would we do this? Why would we hydraulically fracture a rock? Hydraulic fracture treatments are used to increase the productivity index in a producing well or the injectivity index of an injection well. So what is the productivity index? Well, we commonly refer to it as J, and it's a measure of the flow rate we will get from the well depending upon the pressure drawdown we put on the well. So the productivity index is measured in stock tank barrels per day per PSI of drawdown. Q is the surface flow rate at standard conditions, hence stock tank barrels per day. PE, or P sub E, is the external boundary radius pressure in PSI, commonly referred to as the reservoir pressure. And P sub WF is the well sand face pressure at the mid-perfs, commonly referred to as the bottom hole flowing pressure in PSI. So why would we frack a well? Well, hydraulic fracturing can increase the flow rate of oil and or gas from low permeability reservoirs. It can increase the flow rate of oil and or gas from wells that have been damaged due to drilling, completion, or possibly workover operations. It can connect the natural fractures and or cleats in a formation to the wellbore in a fractured formation. It can decrease the pressure drop around the well to minimize sand production. And it can enhance gravel packing and sand placement using a procedure we commonly refer to as a frac pack. So when we frac a well, what data do we need to consider? Well, we need the data required to run both the fracture design model and the reservoir simulation model, and it can be divided into two groups. There is data that can be controlled by the engineer, and there's data that must be measured or estimated but cannot be controlled by the engineer. So we have to develop these data sets, and the primary data that can be controlled by the engineer include the well completion details, sometimes referred to as the wellbore schematic, the treatment volume that we pump, the pad volume that we pump, the injection rate that we pump it at, the fracture fluid viscosity, the fracture fluid density, fluid loss, and any other additives that we add to the fracture fluid, the propping agent type, and the propping agent volume. Now, the other data that must be measured or estimated includes the formation depth, which is sometimes the true vertical depth is used, the formation permeability, the in situ stresses in the pay zone, the in situ stresses in the surrounding layers, the formation modulus, the reservoir pressure, the formation porosity, the formation compressibility, the reservoir thickness. If we look at all this data, and the most critical data for the design of a fracture treatment, and roughly in the order of importance, are as follows. The in situ stress profile, the formation permeability, the fluid loss characteristics of the rock, the total fluid volume pumped during the frac job, the propping agent type and amount used, the pad volume, the fracture fluid viscosity, the injection rate, and the formation modulus. Now, if we want to look at candidates or wells that are candidates for hydraulic fracture treatments, we can say that the best candidate wells for hydraulic fracture treatments have substantial reserves, but need to increase the productivity index in order to be economically successful. On the other hand, reservoirs that are poor candidates for hydraulic fracturing are those with little and/or no oil or gas in place because they're thin reservoirs, or they have low reservoir pressure, or they have a small aerial extent, which translates into a small reservoir volume. Now, unconventional reservoirs, these so-called shale oil and gas reservoirs, are an exception to these rules because economically extended reach horizontal drilling has advanced and is now relatively inexpensive. Massive hydraulic fracture treatments using inexpensive fluids and inexpensive proppants work well on these unconventional reservoirs. And we have made many advances in rigless completion systems, including wireline and coil tubing and ported frac sleeves that can be operated downhole from the surface. So next, how do we design a frac job? We need to choose fracturing fluids. We need to choose proppants. And we need to choose pumping equipment. Let's look at the properties of the fracturing fluid. The ideal fracturing fluid should be compatible with the formation rock and fluids, generate enough pressure drop down the fracture to create a wide fracture, be able to transport the propping agent into the fracture, break back to a low viscosity fluid for cleanup after the treatment. That's to say that the fracturing fluid will have a high viscosity while pumping into the formation, but after the pumping stops, it will have a breaker in the gel that will allow the viscosity to break back to low so that it will flow back easier. And it must be cost effective. The family of fracture fluids available or readily available consist of water-based fluids, oil-based fluids, acid-based fluids, and foam fluids. The foam fluids generally contain some gas in them, either nitrogen or carbon dioxide. Now, just like with drilling, completion, and workover fluids, there are a number of additives that can be added to the fracture fluid depending upon what function that needs to be formed. Anything from a biocide that will kill the bacteria to a fluid loss additive that will improve the fluid loss efficiency, or a friction reducer that reduces the friction. But many different types of additives that we can use to add to our fracture fluid. So now let's talk about the propping agents and how they affect the fracture conductivity or the permeability of the fracture itself. Propping agents are required to prop open the fracture once the pumps have been shut down and the fracture begins to close. The ideal propping agent is strong, resistant to crushing, resistant to corrosion, has a low density, and is readily available at a low cost. The products that best meet these desired traits are silica sand, resin-coated sand, and ceramic proppants, which are man-made. Now, if we look at a plot or a chart of the effective stress that is going to be applied to the proppant after the pumps are shut down versus the fracture conductivity measured in millidarcy feet, which is going to be what determines the productivity index of the well after fracturing, we can see that as the effective stress increases, which is again approximately equal to the minimum yield stress, that the higher the effective stress, the lower the fracture conductivity is going to be. And for silica sand, Jordan sand being a common one, that if you apply too much effective stress to it, it's going to crush and your fracture conductivity is going to drastically fall. Whereas if you use one of the man-made ceramic proppants, then it is much stronger and the effective stress has a much lower effect on the fracture conductivity. So in general, we use the sands for the shallower wells, and we use the ceramic proppants for the deeper wells. Of course, the sand is much cheaper than the ceramic. Now let's look at the equipment. Here's a picture of what we call a common frac spread that includes all the major components required for the frac job. And they include the water tanks that hold the fracturing fluid, the chemical tanks that provide all the additives for the fluid. You have the proppant handling components, and you have the blenders, which blend the water and the sand and the chemicals, and then transfer that to the high pressure frac pumps, which sends the slurry downhole. And all of this is monitored and controlled using a frac monitor van. So what does a typical frac design include? You have a pad volume that is used to propagate the fracture. You have a slurry volume, which is the blended fluid and prop, and it is placed behind the pad or in the next stage to hold open the fracture. And you need a displacement volume to clear the slurry out of the wellbore down to the top of the formation being fractured. If we look at a typical job design and look at the many different things that we are monitoring and recording during the job, we can see that we have the treating pressure here in red, which is your pump pressure. We have the slurry rate, which is in blue, which is the rate at which we are pumping the job. We have the bottom hole proppant concentration in this dark green, and you can see that the bottom hole proppant concentration lags in time behind the surface proppant concentration, which is in the lighter green. And if we are using a compressible frac fluid, or one that has some gas in it, then the bottom hole concentration will be much different, or can be much different, than the surface concentration. We also have what we call the backside pressure. If we are fracking down tubing, where the tubing in a pracker is isolating the tubing pressure from the production casing pressure, then we will often apply pressure to that annulus to back up the tubing pressure. And we have stage slurry volumes shown in this violet or purple. And the stage slurry volumes, as we spoke about before, are the pad stage, and often we will have multiple prop concentration stage, and the last stage will be the slurry displacement stage. So these are all recorded during the time that the job is going on. So how do we predict where these volumes will go? Well, we build a model, and this model includes the sand, typically where the zone where we are going to perforate, and it will be surrounded by other formations and eventually by some shales that will bound or these formations. And we assign these many values that we've talked about before to each layer in this model. So we develop our data sets, and then using our model, we design a fracture treatment. Most engineers now use what is called a pseudo three-dimensional, or a P3D model. And to use the P3D model, as we say, the data must be entered layer by layer to build our reservoir model. When developing these data sets, we know that the fracture treatment would be started in the sandstone reservoir, and the fracture will typically grow up and down until a barrier is reached to prevent further vertical fracture growth. In many cases, you will have a thick marine shale that will be the boundaries to your vertical fracture growth. So how do we optimize this fracture design process? Well, we use a reservoir simulator, which is focused on the cumulative production versus time, and we use a hydraulic or hydrofrac simulator, which mirrors the data with the reservoir simulator, but it is primarily focused on treatment volume versus fracture length. Now we know the method used to optimize the size of the fracture treatment, and it clearly shows the following, and that is, as the propped length of the fracture increases, the cumulative production will increase, and therefore the revenue from the hydrocarbon sales will increase. We know that as the fracture length increases, the incremental benefit, or the amount of revenue generated per foot of additional prop fracture length, decreases. We know that as the treatment volume increases, the propped fracture length increases. We know that as the fracture length increases, the incremental cost, or the cost per foot of additional propped fracture length, increases. If we combine all of this data, all of this information, then we find out when the incremental cost of the treatment is compared with the incremental benefit of increasing the treatment volume, an optimum propped fracture length can be found in almost every situation. Okay, so we've talked about what a fracture is, why we would frack, how to design a frack. Now let's talk about how do we actually pump a job. After the optimum fracture treatment has been designed, it must be pumped into the well successfully. A successful field operation requires planning, coordination, and cooperation of all parties involved. Treatment supervision and the use of quality control measures will improve the successful application of the hydraulic fracturing. Now, safety is always the primary concern in the field, and it begins with a thorough understanding by all parties of what their duties are. A job safety and environmental analysis performed prior to the job is the best means of accomplishing this. Safety meeting is always held to review the treatment procedure, establish a chain of command, ensure everyone knows his or her job responsibilities for the day, establish a plan for emergencies. Screen out is one of the more common emergencies that occurs during a frac job. And screen out refers to a condition when continued injection of fluid inside the fracture requires pressures in excess or larger than the safe limitations of the wellbore or the wellhead equipment. If we look back at our job design plot, we can see an example where we are pumping the job and time goes along, and then we see a sudden rise in our pump pressure, a sudden and unexpected rise in our pump pressure. And at the same time, we have not increased our injection rate. So this point in here is the point where we start to predict or suspect that we are going to have a screen out. If this pressure rises suddenly, then you have to be able to react quickly to this emergency and sharply decrease and finally shut down your pump rate. and allow this pressure to bleed off or leak off into the formation. So that's a common emergency procedure that you have to plan for when you're pumping a frac job. The safety meeting also should be used to discuss the well completion details, the maximum allowable injection rate and pressures, the maximum pressure to be held as a backup on the annulus if applicable, all casing, tubing, wellheads, valves, and weak links such as liner tops should be tested thoroughly before starting the fracture treatment. Mechanical failures during a treatment can be costly and dangerous. All mechanical problems should be discovered during the testing and repaired before pumping the fracture treatment. Before pumping the treatment, the engineer in charge should conduct a detailed inventory of all the equipment and materials on the location. This inventory should be compared with the design and the prognosis. This is your quality control and quality assurance. And then after the treatment has been concluded, another inventory of all the materials left on location should be conducted. In most cases, the difference in the two inventories can be used to verify what was mixed and pumped into the wellbore and the hydrocarbon-bearing formation. In addition to the inventory, another quality control is to take samples of the base fracturing fluid, which usually is water, and have it analyzed to make sure it had the properties that you were expecting. Okay, so now, last but not least, how do we analyze or evaluate our frac job? We have two methods. We have a direct far field technique, which means we're actually going to measure the job while we pump it. And we have an indirect fracturing modeling technique where we use the data after the job. One of the most common direct far field techniques uses acoustic or seismic energy or data that is measured while the job is being pumped. And these data collections can be done either at the surface or more commonly downhole in a wellbore nearby the wellbore that's being fracked. But you can take this acoustic or seismic data and use fracture modeling software, and that will incorporate the events, magnitude, and geomechanical analysis to help determine the fracture size and orientation. It can also estimate the stimulated rock volume. It incorporates the magnitude, the rock properties, and the fluid properties to map the hydraulic fractures that are created. And it can be used to estimate the propped half length or the length of the fracture. Well, because the fracture treatment data and the post-fracture production data are normally available on every well, these indirect fracture diagnostic techniques are most widely used compared to the direct fracture techniques, and they are used to determine the shape and dimensions of both the created and the propped hydraulic fracture. Indirect fracture techniques consist of hydraulic fracture modeling of net pressures, pressure transient test analysis, and production data analysis. The fracture treatment data can be analyzed with the pseudo 3D fracture propagation model to determine the shape and dimensions of the created fracture. The P3D model is used to history match the fracturing data, such as the injection rates and the injection pressures. Let's talk about net pressure, because net pressure is one of the best indirect methods to analyze a fracture treatment. It is used as a fracture propagation model to analyze the net pressure measured during a fracture treatment. In many formations, the pressure drop down the fracture is dominated by the pressure increases near the tip of the fracture as propagation occurs. The net pressure profile controls both the fracture height and fracture width distribution along the fracture length. You will often have a near wellbore pressure drop due to the completion, and it has to be accounted for. But remember, the net pressure is a bottom hole pressure. So it is the surface pump pressure plus the hydrostatic pressure plus the friction pressure down the pipe. But if we take this data and we put it into our P3D model, we will get a profile or a picture of the fracture height, the fracture length, and the fracture width using this net pressure analysis. Now, another indirect method called a post-fracture well test analysis. It is used to compute an estimate of the prop fracture length, the fracture conductivity, and the drainage area of the formation using well test data. Since it is well test data, it's important to keep good records of the flow rates of oil, gas, and water, as well as the flowing pressures, better be bottom hole pressures, after the fracture treatment. And if possible, a pressure buildup test should be run after the well cleans up following the fracture treatment. So this concludes the presentation portion of today's webinar. And in a moment, we will move to the question and answer session. But first, I want to invite everyone to attend my 5-day online course on hydraulic fracturing. And this course is going to be held on 2 dates. The first one from the 12th to the 16th of October in 2020, and the next one on the 11th to the 15th of January in 2021. And to register, you simply go to register@petrotech.com. But this course teaches an understanding of the concepts and practical knowledge of how to get an optimum design of hydraulic fracture treatment for various types of reservoirs in order to improve the well productivity. The course will cover the physics, chemistry, job design, execution, and post-treatment evaluation. And recognition of well candidates for stimulation is emphasized. The course is designed to provide attendees with a working knowledge of fracturing design and fracturing procedures, and they will learn the practical application of different types of fracturing jobs and the use of additives to produce specific fracture fluid properties. We'll also learn how to evaluate the success or failure of a fracture job. The objectives of the course are hydraulic fracturing selection criteria, determining in situ stresses, fracturing fluids and additive properties and selection, proppant properties and selection, hydraulic fracture treatment design, acid fracturing, hydraulic fracture treatment execution, and post-treatment evaluation. And below is the information on the course price.